Okay, so in this section, we're going to talk about exponential and log functions. So we're going to cover section 6.3 through 6.6. Again, this is going to be the condensed version that you will need for your exam. So first of all, let's talk a little bit about the graphs of these functions, okay? So again, if we understand the graph, then it's a lot easier to look at what the equation means, okay? So first here we have y is equal to 10x. So this is called an exponential function, okay? So this is an exponential function right here, right? So notice that it starts off slow, then it gets to a particular point and then it just skyrockets, okay? So again, this is an exponential function. And you can have, it doesn't have to be 10 to the x. It can be 2 to the x, 3 to the x, 4 to the x, 5 to the x. It can be any number there. Okay. All right. But it gets tricky if it's numbers that are negative. But anyway, anything one and above, we should get something like this. Okay. All right. Now, this other graph here is called the log function or logarithmic function. Okay. So this one right here. Okay. It's a logarithmic function. And so basically the log function, okay, it is a reflection of the exponential function. So that's why I have here in the middle, y is equal to x. Okay. So the inverse of a exponential function is a log function. Basically, that just means it reflects it over y equals x. Okay. Just like our previous example in the last section. All right. Now, if we look, if we start, plugging in numbers for the log function, can we just put any number in there? And the answer is no. So let me check my calculator here. All right. So if I go to my calculator and I look for the log part of my calculator. So if I put in, say, log of 1, okay, it's going to give me 0. Log of 1 is 0. Again, this is not drawn to scale. Okay. If I put in log of 2, right, it gives me a number, log of whatever, 58, all right, it gives me a number. However, what happens if I put in, say, log of 0? All right, and I need to move the calculator up a little bit. Okay. So if I put in log of 0, it's going to give me an error. Okay. And let's say I put a number that is less than 0. So let's say I have log of -1. All right, it still gives me an error. Why is that? Well, let's look at the graph, right? So it looks like there is some kind of vertical asymptote on the y-axis. So notice how the graph is just as it gets to the left, as it graphs it to the left, it just keeps going down, down, all right, on the y-axis, but never crosses it. So it looks like there is a vertical asymptote at the y-axis or x equals 0. So that's why if you try to put any number 0 or anything lower than 0, okay, it's going to give you an error because the graph doesn't exist there. That's why I said I can't calculate this because there's nothing to calculate. All right. So um, so again, the bottom line here is that if you have the form y is equal to 10x, okay, then that's an exponential function. And you have the form y equals log of x, then that's a log function. And now another thing I want to point out is that on the log function, so like for example, if you just have x, right? Technically this says x to the first power, kind of like, x squared, x to the third, right? But we don't write the 1 there as a power. We just automatically assume that that is a 1. Okay. Same thing here. So the base of this function is actually base 10. Right. So if I wanted to change the base, then it would be like log of base 3 of x. Okay. Or y is equal to log of base 4 of x. Okay, so what I'm saying is if you don't see a number here, this is the base area. In this area here, it's automatically base 10. Okay, so let's keep exploring this log function and try to figure out, okay, what is the domain, the range, and the asymptote of these types of functions. So again, I'm going to focus on log function here. Well, as I mentioned before, okay, that if we put in numbers that are 0 or lower than 0, then it's going to give us an error. So if they're asking for the domain of this log function, okay, we're going to focus on the x. And what we do is we're going to set x, or whatever is inside here, to greater than, and it cannot equal 0, because remember, log of 0, it doesn't exist because there's a vertical asymptote there. So we set it to x is greater than 0. Okay? So, and then that will be our domain, or we solve for x. So for example, if I have log of x minus 1, okay, and they want the domain, then all I got to do is I take the x minus 1 and I set it to greater than 0 and solve for x. And then this becomes as x, oops, as x is greater than 1. That will be my domain, as that's my answer. Okay? So let's do it again. So if I have y is equal to log of x minus 5, okay? So I just focus what's inside the parentheses. And in the parentheses, it says it's x minus 5. So I set that to greater than 0 and then solve. Add 5 to both sides and I get x is greater than 5. And that's it. That's my domain. All right? So when it's asking for the domain of a log function, you just focus what's inside the parentheses, all right, in these types, in these scenarios, okay? Because it gets a little bit more differently when we're talking other other functions inside the parentheses. But as long as it's a linear, x minus 1, x minus 5, or 2x, to the first power, then you can do this, okay? All right, so now let's um, extend this a little bit. And what happens if we add something to the log function? So for example, let's say we have y is equal to, say, 2 log of x minus 7 plus 3. Okay, so we have this. It looks complicated, but it's not that bad. Okay, so again, they want us to find, let's say, the domain. Well, again, what do we focus on when we think about the domain? Inside the parentheses, right? We look inside the parentheses for the domain. We look in here. So what do? We take the x minus 7 and we set that to greater than 0. And then that gives us, add 7 to both sides, and we get x is greater than 7. And then that will be the domain of the function. Okay? What if it asks for, say, the range now? Well, let's go back to the parent function, right? Y is equal to log of x. The range of this, okay, it goes, obviously it goes down to negative infinity, right? The range goes to negative infinity, the log function. In regards to the highest part it goes, well, this graph will continue to keep going, even though it's going to be slow, right? It's going to keep going up and up and up and up and up and up. All right. So it's going to keep going up. All right. So the range is in regards to the highest point, it's going to go to positive infinity. Okay? So in this case, for the original function here, the range of this is going to go from negative infinity to positive infinity, always. Okay? If I go back to this graph here, okay, well, all this other stuff is just fluff. What do I mean? Well, we know x minus 7, right? That means it's going to go to the right 7. And then the plus 3 means it's going to go up 3. Okay, that's what the plus 3 does. And then the 2 is it's just going to extend that by a factor of 2 in the y direction. So basically, this graph here is going to look, something like up here somewhere. Okay, it's going to look somewhere up here somewhere if I extend this coordinate plane. Okay, so notice that the range is still going to be what? Negative infinity to positive infinity. Okay, so it doesn't matter what you do to it, right? Again, as long as it's in this form, the range in this case will still be all real numbers from negative infinity to positive infinity, even though I moved it to the left, right, stretched it, because it still has that form. Okay? That's the range. Now, what about if it asks for the asymptote? All right, so I'll just A for asymptote. Let's go back to our parent function. So remember I said that this graph here, as it goes to the negative direction, it doesn't pass the y-axis, or in this case, x equals 0. All right, so the asymptote here, the asymptote, trying to find there. Okay, so the asymptote here, okay, for the original function is going to be at x equals 0. Okay. In fact, whatever you find, whatever you get for the domain, whatever number it is going to be, that's going to be the asymptote. So for example, in this case here, we had the domain was x and greater than 1. So that means the asymptote here is going to be x is equal to 1. This one here was x is greater than 5. So then the asymptote here is going to be x is equal to 5. So whatever you get for the domain, the number, that is the asymptote. Okay? All right. So in this case here, if you had to make an educated guess, what would be the asymptote for this function? Exactly. 7. Perfect. Exactly. Right. So whatever you get for the domain, right? The domain was x is greater than 7. So the asymptote will just be x is equal to 7. It's always the case. Every single time. It never fails. Right? Again, if you have this type of function. Okay, so I got a couple of minutes left. Let's try one more example here and see if you can get it. Okay, let me pause. Okay, so again, the domain, right? All we need to do, so we have this function here, and we want to find the domain, range, and the asymptote of this function. So the domain, we focus inside the parentheses. So we put 2x plus 3, and then we set it to greater than 0. Not equal to 0, just greater than 0, then we solve. So when we solve this, we get x is going to be greater than negative 3 over 2. Okay? So that's going to be the domain here. That's the answer for that. Okay, the range, again, it doesn't matter what's happening here. This is going up by 8, and then this 5 is going to stretch it out. So that doesn't matter. So the range is always going to be all real numbers. Okay. Now, in regards to the asymptote will always be whatever you get for the domain, that's your asymptote. So in this case, it's going to be x is equal to negative 3 over 2 every time. Okay, so whatever you get here, it's always going to be the same thing. Okay, so let me go and talk about the last point here because it's important. So another way to write this, so we talked about this here, right? Y is equal to 10 to the x if we reflect it over y equals x is equal to y equals log of x. What happens if I change the base to what's called e? E is just a number, e to the x. If I put that in the calculator, okay? If I put that in the calculator, is it at? I think it's this one right here. Okay, e. If I put e to the 1, shoot, try that again. E to the 1. It's just going to give me 2.718. It's just a number. E is just a number, just like pi. Pi is 3.14. E is just 2.718. Okay? So it's the number comes up a lot, especially in financial mathematics, that it just is represented by that number. So anyway, but it's the graph is the same as an exponential function. Okay? All right, that's why I didn't change anything. It's the same type of graph. Now, if you were to reflect that over y equals x, just over here, you get what's called ln of x. Okay? And so it's a logarithmic function. Okay? In this case, the base is going to be e. So if it doesn't say it, it's still going to be, it's going to be base e. It's always base e, actually. Okay? All right. So that's why in the other problem, okay, when I wrote it down here, I had originally wrote 5 ln of 2x plus 3 plus 8. They interchange those. Okay. But in this case, if it's ln, the base is e. If it's log, then the base is 10. That's the difference. Okay. So, but the way you solve an ln function and a log function is exactly the same thing. Okay. So again, if you have y equals e to the x, the inverse of that will be y ln of x. And then the base of this is always going to be e. And again, that number just means 2.718. What I want to talk about is this next part. So make sure you go over this on the next part, is these exponential and log properties. Okay? So this one here says, if I have a log, I can rewrite it as a to the y equals x. If I have a log and this is x times y, I can separate that as log of x plus log of y. If I have a division here, then I can separate it as log of x minus log of y. If I have a power here, right, x to the r, then the r I can put it as a front. And this one says if it's a log of x, it's just going to be x. If the bases here are the same as well as this one here, it's just going to be x. If I have log of 1, that's equal to 0. If you have log of a of equal to 1, again, I mentioned this already, the log of x, if it's not there, it's log 10. Then the ln of x, the base there is e. And this one's called a change of base. I know I went through that pretty fast, but familiarize yourself with this one, okay? Because that's what we're going to talk about next, on next class. All right, but I just wanted to at least give you a glimpse of what this is talking about.